Okay, well, maybe this time everything will work out. Sorry for the technical difficulties. Once again, my name is Yue, and I'll be speaking about a CostAware logical framework, joint work with John Sterling, Harrison Grodin, and Robert Harper. Let me begin with an observation about using dependent type theory for program verification. As a verification framework, dependent type theories are unique in the sense that programs may be analyzed using the same logical language that they're written in. Although this perspective is widely applied to analyze extensional or behavioral properties of programs, typically one cannot apply the same idea to obtain an intrinsic account of intentional properties, such as cost or complexity. Assuming the type theory we're working in is computationally adequate, the fact that f is a function means that, to see this, let f be any candidate cost assignment that maps a Boolean computation to a natural number expressing the cost incurred. Assuming this type theory we're working in is computationally adequate, the fact that f is a function means that its image is determined by the two canonical Booleans. Clearly, this contradicts one's intuition about how a cost assignment should work and illustrates an important fact in type theory. Equal programs are not distinguishable. But because of the dual role of programs in type theory as functions and algorithms, this naive view of cost analysis forces one to consider programs that are equal as functions, but distinct when considered as algorithms. In this talk, we present CAF, a CostAware logical framework for programming and specification of both cost and behavior. As discussed, such a framework must resolve the predicament of speaking of equal programs with different computational costs. Sorry, I'm getting out of sync a little bit. For instance, on the one hand, we would like to be able to separate sorting algorithms by the number of comparisons they use. On the other hand, we would like to identify all such algorithms by using an extensional equality specification whose concern is only input-output behavior. In general, the ability to speak of extensional or behavioral properties is not only important for expressing program specifications, but also necessary for developing ordinary mathematics. Therefore, any foundational cost analysis framework must support both reasoning about programs in an extensional manner and an intentional manner. Recalling our basic observation about the naive approach, the problem is that the traditional view of cost as a property only makes sense for raw terms, a concept that is unavailable to type theory internally. The type theoretic ethos is to promote cost from a property of raw terms to a structure attached to type terms that one may manipulate inside the theory. At a high level, CAF combines this shift of cost as a proof irrelevant property to a proof relevant structure with several recent type theoretic developments and furnishes an expressive language for both cost analysis and behavioral verification. In particular, CAF programs enjoy a noninterference property that ensures cost structure does not interfere with program behavior. Before diving into the details of CAF, let's review the standard way of encoding cost structure using cost monads and see where things break down. Let C be a monoid that encodes the cost structure we have in mind. The cost monad induced by C is just the associated writer monad, in which the monad structure is given by the monoid structure. A CostAware program in the setting is a tuple consisting of an ordinary program instrumented with a cost component. However, there are two problems in the setting of cost monads. First, it is cumbersome to express extensional equality of programs, a problem that becomes amplified at higher types. A more subtle problem is that one may write down exotic CostAware programs from which one cannot extract an ordinary program. For instance, one may define the following program F that outputs true or false depending on whether the cost component of the input is 0. In other words, this encoding of cost structure with cost monads does not satisfy the non-interference property of intension and extension. Now I will discuss how these two problems are resolved in CAF. In CAF, we think of cost as an abstract computational effect, which prevents one from defining exotic programs as illustrated previously. Concretely, this computational effect is expressed in a call-by-push value language, a paradigm organized around the dichotomy of values and computations at both the term and type level. Semantically, value types are interpreted as sets and computation types as algebras over the cost monad, and this pair is arranged in a free forgetful adjunction whose functors form the semantic counterpart to the type constructors that bridge the value computation dichotomy. To implement cost structure, we axiomatize a single effect called step, which, as the name suggests, incurs a given cost onto the given program. Accompanying the step effect are equations governing the coherence properties with respect to the cost monoid and the interaction of step with other computations. For instance, step 0 states that taking a step with 0 cost is a no-op, and a bind step states that sequencing commutes with step. Equations like these allow one to define cost refinements in CAF. For example, one may define the has cost refinement, which states that a computation has cost C exactly when it is equal to a canonical computation that takes C steps. In a similar fashion, one may also define the is-bounded refinement that allows weakening of the witnessing cost. Moreover, one may reason about these cost refinements compositionally by proving standard syntax-directed lemmas that derives the cost bound of a computation from cost bounds of its constituent computations. Now, to reason about the behavioral property of programs, we may enter a special program phase called the extensional phase in CAF. More specifically, we extend the language of context with a special proposition called the extensional lock. And we may think of the extensional phase as the collection of contexts in which we possess a proof of the extensional lock. The force of the extensional phase is realized by an axiom that trivializes the cost effect whenever one has a proof of the extensional lock. Thus, intuitively, one may think of the extensional phase as of CAF as an ordinary extensional type theory. For instance, in the extensional phase, we may prove that merge sort and insertion sort are equal under the comparison cost model. Crucially, this equality does not hold outside of the extensional phase, a consequence of a meta-theorem we will see later about CAF. The extensional phase of CAF is inspired by recent work of Sterling and Harper on a type theoretic reconstruction of the phase distinction in the theory of program modules. In its original context, the phase distinction is about breaking dependence of static components of a module functor on the dynamic components of the input module. Replacing static component with extension and dynamic component with intension, we see that the phase distinction is also present in the CostAware setting in the form of a non-interference property. The behavior of a CostAware function should not depend on the cost component of its input. To state and prove this result as a theorem in CAF, we introduce the extensional and intentional modality, which extracts and seals away the extensional part of the program, respectively. First, the extensional modality is defined by exponentiating the extensional lock and is written here as an open circle. As a reader monad, the extensional modality has a unit given by weakening. Now suppose that we have two programs F and G. We may check that the equality of the inclusions of F and G is equivalent to the equality of the original programs in the extensional phase. In other words, we may use this extensional modality to extract the extensional part of a program. On the other hand, the intentional modality is defined as a certain pushout or a quotient inductive type, here indicated as a closed circle. Intuitively, one may think of closed of A as a copy of A with the property that it is isomorphic to the unit type in the extensional phase. In other words, the intentional modality seals away the extensional content of programs and makes a type purely intentional. A useful way to remember this is that pure intentional things have no extension. Using these two modalities, we may state and prove the noninterference theorem. Any function from closed of A to open of B is constant, which illustrates that in CAF, the behavior of a program cannot depend on the cost of its input. Switching gears, let's discuss the process of defining and analyzing algorithms in CAF. As a type theory, CAF is well equipped to express programming constructs rooted in mathematical principles, such as structural induction and recursion. In this setting, programs are manifestly total, and there is no native support for general recursion or partial programs. On the other hand, algorithms in the wild are decidedly less well-behaved and fully embrace general recursion, whence termination is not immediate from their presentation. Our experiments with CAF, we realized that this tension is resolved in the CostAware setting, in the sense that one may use cost structure to encode general recursion. We have delineated this idea into a recipe that emulates the classic method of recurrence relations and deployed the recipe in a variety of case studies. First, we have in mind an informal description of the algorithm and its associated cost model. We use the given description to define a clocked version of the algorithm in CAF. Here, the clock parameter is a termination measure that decreases at each recursive call. Note that if the clock parameter is 0, the program raises an exception or returns a default value. Consequently, this program may perform recursive calls as stipulated while remaining plainly total. We place steps in this program as prescribed by the cost model. Next, we define the desired cost bound of the algorithm. Because we're not interested in the cost of the cost bound, we may define it however we like and do not place any steps. Now we may instantiate the clocked algorithm with the cost bound we just defined to obtain the complete program. Lastly, we verified that this program satisfies the cost bound using the cost refinements and lemmas we saw previously. Because CAF provides a rich specification language, we're also able to define and verify the behavioral specification of the resulting program, which ensures that our cost bound actually applies to the intended algorithm. We have encoded a version of CAF in the Agda proof assistant as a collection of postulates and rewrite rules. Agda CAF is a light and modular library whose core components are spread across a few small files. In particular, ordinary inductive types of our implementation are directly imported from Agda, allowing us to reuse the Agda library in our case studies, some of which I will highlight here. First, we proved that the number of modulus operations in Euclid's algorithm is bounded by the inverse to the Fibonacci sequence. For sorting algorithms under the comparison cost model, we have also verified the best known bounds for insertion sort and merge sort. Okay, I guess it just jumped to that slide. We can go there. Turning to the meta theory of CAF, let's look at how to define models of CAF. Formally, CAF is specified by a signature in a logical framework furnished by locally Cartesian closed categories. This logical framework consists of a universe of judgments closed under dependent products, sums, and equality. An object theory such as CAF is specified by a collection of constants built from the types in the logical framework, and whose equational theory is expressed using the framework equality. Because it is often following functorial semantics in the sense of Bouvier, CAF is defined as the free LCCC over the signature, and a model of CAF is just a structure-preserving functor into another LCCC. Because it is often intractable to specify the functor and check functoriality directly, we will use the universal property of the free construction to define models, which states that given an implementation of the signature of CAF in the target category, one may uniquely extend it to a structure-preserving functor. The data of this implementation is encapsulated as an algebra over the signature and amounts to an element of the dependent sum presented by the signature. It may be helpful to draw an analogy to the more familiar case of finite product theories. For instance, one may think of groups as group objects in the category of sets, or as product-preserving functors from the associated Bouvier theory. I present a particular model of CAF called the accounting model in any topos with a distinguished proposition E, which serves as the semantic counterpart to the extensional lock in CAF. We will construct this model using the internal language of the topos, which is a dependent type theory that has in particular inductive types, quotients, and a hierarchy of universes. The accounting model is so named because it is a version of the standard Ellenberg-Moore model of call-by-push value. Thus, we interpret value types as a sufficiently large universe and computation types as algebras over the cosmonad whose carriers are types in the same universe. The twist here is to define the interpretation of computations so that the cost component of the programs is sealed away under the intentional modality, which immediately validates the axiom governing the extensional phase in CAF. From the counting model, we may deduce a non-derivability theorem, which states that steps over a cancellative monoid C is not degenerate. For instance, this implies that steps may not be compressed. The cost monoid is the natural numbers. In conclusion, we contribute CAF, a CostAware logical framework for both cost analysis and behavioral verification. Our work emphasizes that in the CostAware setting, one needs a new kind of phase distinction, one of intension and extension. Moreover, we show that CAF programs obey such a phase distinction via a noninterference theorem stated in terms of modalities governing intension and extension. We showed how to encode general recursive algorithms using cost structure and formulated two classic analysis techniques, the method of recurrence relations and amortized analysis. We mechanized CAF in Agda and developed these techniques in several case studies. I didn't discuss parallelism explicitly, but we have implemented an equational presentation of the profiling cost semantics of Belloc and Greiner and used it to verify non-trivial bounds on a parallel complexity of several sorting algorithms. Some directions for future work includes relating the abstract notion of cost in CAF with the traditional operational semantics and investigating opportunities for automation. Thank you for listening.
I thank the speaker. All right, I saw a few questions online. Okay, let me start with the first one. You said the cost algebra is a monoid. Could it have additional structures such as cancellation operation and the framework provides a principled way of taking those operations into effective?
Currently, we just assume that the monoid is an ordered monoid because we're analyzing upper bounds. It could have additional structure, and really all we require is that it has a pre-order relation so that we can analyze upper bounds or potentially lower bounds. Hopefully that answers your question.
Okay, thanks. Let me take one more online question, and then I think I'm going to end this session because the people are waiting. All right. So next question. We know that some algorithms have different worst case and expected time complexities, for example, pixel. Can this concept be formulated in a type of its extended systems?
That's an interesting and very important feature to have if you want to analyze algorithms like quicksort. I believe it is possible to do expected time analysis. It's just that CAF is a framework that allows you to formalize your own analysis methods. It does not have built-in support to, or built-in knowledge about, for example, expected time analysis. But it is certainly possible to express these ideas.
All right. That will be the end of this session. Thanks to the speaker.